Hello and welcome to the Computing Conversations column. This column is from the March 2014 issue of IEEE Computer and is titled Len Kleinrock, the First Two Packets on the Internet. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I'm the editor of the column, and I'm Charles Severance from the University of Michigan. Although it might seem like the Internet has been around since the beginning of time, it did indeed start somewhere. The first two packets ever sent on the Arpanet originated in a lab at the University of California, Los Angeles, and ended up at the Stanford Research Institute on October 29, 1969. I visited with Len Kleinrock at UCLA to learn the story of those first two packets. ARPA funded the Arpanet, the first version of the Internet, because it wanted to make the best use of its research investments, which were scattered in various university campuses around the country.
University of Utah had a terrific graphics operating system. SRI had database. We had simulation. University of Illinois had high-performance computing. And every time ARPA brought on a new researcher, they'd offer to buy him a computer, fine, but the researcher would say, I want the same capability all those other guys have. I want the graphics, the database, and all the rest. And ARPA said, we can't afford that. If you want to do graphics, you log on to the machine at Utah through a network that we think we're going to make. So the need for the network was to do resource sharing and not to protect the United States against a nuclear holocaust.
Building a multi-institutional wide-area network to connect diverse computing hardware would be a significant effort that needed careful coordination.
So they brought in Larry Roberts, another classmate of mine, in fact an officer of mine at MIT, to manage this project. He came to me because he knew my work. He watched me do the simulation. In fact, I used his compiler on the TX2 computer and said, Len, we need to know if this thing is going to work. He knew that I had the theory, so I could show it to him it's going to work. In fact, he even says he would never have decided to spend millions of dollars of the U.S. government's money if he wasn't sure this thing would work.
Len and Larry spent about a year bringing experts together to develop a specification for the new network's software and hardware.
During the design phase, some great people were there throwing their ideas out. Herb Baskin was there, a time-sharing expert. And he said, if this network can't deliver short messages within a half a second, I can't use it for time-sharing. Right. Specification, exactly. Half a second. By the way, we got 200 milliseconds. It came along. And Wes Clark said, separate computer for communications. I said, look, if this is going to be an experiment, and I was also interested in the research and the experimentation, we have to build software in so we can run experiments. Artificial traffic generators, measurement hooks, a place where the measurements can be evaluated, put that software in. So Howie Frank began to talk about network reliability. He said this network, if anything fails, the network shouldn't collapse. So we built in so we didn't say there should be 5 nines of uptime. We went much more pragmatic. We said if any single thing fails, everybody else can still talk. Yeah. So to do that, you need something called a two-connected topology, 2 independent pairs between every pair of nodes.
The design was developed throughout 1967, and in 1968 the team sent out a formal request for proposal. Bolt, Brannick, and Newman, BB&N, won the contract to produce the Arpanet's first switch, and UCLA functioned as the first node and the Network Measurement Center, responsible for testing and verifying the new networking hardware and software.
So all those specs went to BBN. They built the darn thing. They delivered the switch here at UCLA on schedule. 8 months after they got the contract, they were to deliver this new technology, new applications, new device. They did it on time, on budget. It came here, we plugged it in, and bits began to move back and forth between our time-shared machine and that switch on the day after Labor Day, September 2nd, 1969.
The second switch went to the SRI in Palo Alto, October 1969. And once it was connected to the SRI host computer, the team could join the two switches and test them. The initial 50 kilobit per second line was made up of multiple 4.8 kilobit per second leased lines ganged together.
So we decided one night late in October, programmer Charlie Klein and I were in the room and said, look, let's communicate between the two machines. So we got a hold of Bill Duval, their programmer up there, and we said, let's simply log in from a terminal connected to our host to that machine. The idea is these are both time-sharing systems. They expect terminals to connect in and use the services of the machine. The big thing was sit at a terminal here, log onto your machine here, and through this wonderful network, log on here as if you're a local user.
To help debug the new software, the team had an analog audio connection using one of the 4.8 kilobit per second lines between UCLA and SRI. They watched both systems and the communication channels very carefully as they started the test.
Charlie typed the L. He said, "You get the L?" Bill said, "Yep, got the L." Typed the O. "You get the O?" We're trying to do LOG for login. Get the O? Got the O. Type the G, get the G, crash. So the first message ever on the network was low, as in lo and behold.
For all the years since 1969, Kleinrock has kept Interface Message Processor Serial Number 1 at UCLA. There has been discussion of putting it in the Smithsonian, but he wanted to ensure that the IMP was always on the display for public to see. It currently sits in Boltner Hall, in the exact room where those first two packets were sent from UCLA to SRI. The room has been restored to look exactly as it did in 1969. Even the architects at UCLA are finding ways to commemorate the historic events that happened that day in Boltner Hall.
Now that's especially interesting because if you go outside this hallway here, down into the alley, and come into another entrance to this building, and I just discovered this about a week ago. You walk on a platform, and there's a mosaic of tiles down there, and they're a strange pattern. It turns out it's the ASCII code for lo and behold.
Although UCLA was initially responsible only for the testing and measuring of the Arpanet, over the next decade it assumed leadership of the Arpanet effort as graduate students including Vince Cerf, Steve Crocker, John Postel, and Charlie Klein became the project's leaders, managers, and developers. Initially, BB&N saw the Arpanet and IMPS as a black box product, but ARPA ultimately forced BB&N to open the system's source code.
We could break it at will, as I said, and every time we did, we would call BB&N and say, "Fix it, we did this, fix it," because they wouldn't give us the code. They kept it proprietary until ARPA said, "We paid for that code, you have to open it." They did, we saw it. Every time we got it, and it would take them 6 months to fix anything.
Right.
We discover a fault this time we had the code. We showed them how to fix it. Still took 6 months.
Over time, the project moved to a more open-source approach overall and drew its technical directions and leadership from the growing Arpanet community.
One of the things I was very much interested in design was distributed control. Why?
Right.
Well, I was a student of Shannon. And Shannon's great work came when you had a lot of things interacting, long code words, for example. That's when these emergent properties arise. So I said, I want to design large networks. Design a large network. You can't have a single point of control. You have to distribute it.
Right.
So what does it mean to distribute control? You're delegating authority to all the peers.
ARPA believed in the researchers involved in the project and gave them a lot of autonomy.
When ARPA started funding the principal investigators, they had the same philosophy. They said, look, you're a smart guy, here's some money, go do the thing you do best. We're not going to sit on top of you. Make good things happen. So here we are, I'm a recipient of that kind of money. What do I do with it? I've got my graduate students. They're brilliant kids. Look, we need a host-host protocol. Here. I'm not going to sit on top of you. I'm going to run with it. That is not a product mentality.
Right.
That is a research and development to create at the time. And it worked so well.
It certainly did work well, and after nearly 45 years, the notion of distributed control, emergent properties from large networks, and delegating authority to our peers makes it possible for us to almost forget that perhaps the most complex collective engineering endeavor humanity has ever attempted works so well we barely notice it anymore. Lo and behold, indeed. This column is from the March 2014 issue of IEEE Computer and is titled Len Kleinrock, the first two packets on the Internet. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I'm the editor of the column, and I'm Charles Severance from the University of Michigan.